Okay, it is time to do some calculus. This is question number 1 in your packet of free response questions. It's from the 2005 AP test, and it's problem number 2 is what it's telling us. So if you're looking at that, then you're thinking that problem number 2 is a calculator question. 1 and 2 are traditionally or always calculator questions. So right now, pause and get your calculator if you don't already have it. I'm going to be talking you through things to do in your calculator, and please make a note if you're confused. I can't actually show it because I'm working off of my iPad and I can't show the calculator on there. But please, please, please make sure that you're getting the answers. If you're doing this and just writing down what I'm doing, you're missing half the point of it, because we do need to be able to do things in our calculator. I know a lot of times they don't let you use your calculator, but you got to be able to do it. It's going to actually get you the answers. So this is a great question to look at. It's a little bit different twist. If you look right off the bat, I'm observing that we have 2 different functions here, potentially looking a little scary. And that's why I told you to hold off on this one. But 3 of the 4 parts of this are directly from chapter 6. And the 4th part is something we need to review anyways. So this is an outstanding question for us to talk through. Feel free to pause the video and try it yourself first if you want that challenge. If you're going to be totally freaked out by it, then just walk through it with me and make sure you're thinking through and making sense of it. Now that you have your calculator out, I would go ahead and let's type into our y equals. Good rule of thumb, whenever you have a free response question, since you have 15 minutes to do these, take 10 seconds at the beginning and type in any functions you're given into your y equals, because chances are you're going to want to graph it, you're going to want to find multiple values, and we've looked at how it's easier to just find those on the calculator by calling up your y1 function rather than typing it all in. You're going to make less errors. So let's type those 2 functions into y1 and y2. So I'm making the first one y1 and the second one y2, and then go ahead and check and make sure your mode is in radian mode, because I'm seeing that we have a trig function here, and in calculus we live in radian mode, so especially those of you that are in physics. Okay, I'm glad you got those in your calculator. Now let's go ahead and read through and see what's going on here. We've got Tide removing sand from a beach at a rate modeled by the function r. So r is my removal of sand. Pumping station adds sand to the beach at a rate modeled by the function s. So if you just think about the concept here, we have sand being removed and sand being added at the same time. I'm wondering right now, is the amount of sand changing? Is it a positive change? Is more sand being added than removed, or vice versa? And there's a possibility that both are going on depending on the time. Both R of t and S of t have units of cubic yards per hour. So sometimes I like to jot that down. Of course, this is the part of my problem that's not getting scored. This is just me looking at the problem. So these are just notes to myself. And we've got t is measured in hours from 0 to 6. At time t equals 0, the beach contains 2,500 cubic yards of sand. Important to note, what you just read or heard me read was given initial information. So another way of saying that, I don't want to say R of 0 or S of 0, but let's just use a general F. Where F would be my function for the amount of sand on the beach. I've got 2,500 cubic yards of sand, okay? That's not directly related to my rates, but we'll get there. I think we're ready to start part A. How much sand will the tide remove from the beach during this 6-hour period? Indicate units of measure. And I think I told you when we were going through one question, if you look at the number of sentences that are in each part of your free response question, a lot of times that is an indicator of how many points you're going to get for the question. So if we're looking at part A, I'm picking out that part A is going to be 2 points. How much sand? That's your 1 point. And then your second point, you're going to get a point for putting units with your answer and getting the answer. So we're looking at how much tide is being removed from the beach. And hopefully after we talked through the problem, you're recognizing that as referring to the first function that's talking about removal of sand. The second function is talking about sand being added. This has nothing to do with it. They're not asking how much sand is on the beach, how much is removed. General rule of thumb here is to think when I integrate a rate, I get an amount of something. So we've talked a lot, obviously, about integrating velocity. Rate of change of distance with respect to time gives us amount of distance change, accumulated distance change, or distance traveled. But we're moving past that, which means that I can put any rate in there and I can get an amount of change in it. So how about we take our integral of our R function, which is the rate of removal of sand, and that's going to give me the amount of sand removed. So I've got to be a little bit more specific here. It's during a 6-hour period, so I'm going to go from time 0 to time 6. Integral of rate is going to give me, let's go ahead and type that in our calculator. So I'm on my home screen right now of my calculator. And recall that your integral is option 9 under the math button. So math 9. And if you have the newer calculators, they're of course going to look exactly like what I have on the screen here. If you have the older calculators, it's going to give you some command like this for function integrate, and then you're going to type in y1, comma x, comma 0, comma 6 is going to give you the same thing that we have right here. And again, my rate 1 is, my R of t is in my y1 function. So I would just put y1 there rather than retype the function. Answer check, you should be getting 31.816 for your answer. Again, we got to be in radian mode to get that answer. To put units with my answer, that's going to be cubic yards. And they didn't really say that you need to explain what your answer means. I would probably put 31.816 cubic yards is the amount, I'm abbreviating for space here, of sand the tide will remove during the 6-hour period. And I'm really just using general test-taking strategy. Answer the question by rephrasing the question and putting it into a sentence. So that is, ignore this first part. What I have in red right here is really my answer to part A of that question. Moving on to part B. B, write an expression for, and again, that was 2 points. So if we want to keep track of our points here, we did say that this one was 2 points. Part B, write an expression for y of t. So y is just another variable they're introducing, for the total amount of cubic yards of sand on the beach at time t. So this goes back to my initial thought of, what's the total amount going to be? Is it actually decreasing? Is it increasing? And that might depend on what time we're at in the interval. So we need a function or an expression for the amount of sand on the beach. Well, it appears like in part A, we actually helped ourselves out a little bit because we have an expression. If you go back to before we calculated, and we say that this is just some general time t, we could say we have an expression for the amount being removed. And then, of course, we have our other function, which is telling us how much is being added. So here's where integrals really start to help me out a bit. And I'm going to go to, and we'll stick it on this page. Just go up and down. Do a different color here. So part B, y of t, my amount on the beach, is going to be a combination of how much I started with, how much is being added, and how much is being removed. So all I know so far is how much is being removed. here's what it's going to look like. I'm going to write it down since this is kind of our first time of doing one like this and see if you can follow. I'm going to start with my initial amount. That's how much is actually there on the beach, 2,500. And if I go back to this for a second, that's what I put in green up here when we were talking about, and I had used F. It appears that Y is my variable that they want me to use. So 2,500 plus the amount being added to the beach is modeled by my pumping station function. That'd be my S of t. So the integral of S of t is going to give me the amount, integral of my rate of change of how much is being added. And that's going to be from 0, instead of to 6, I'm going to do from 0 to t. And then I'm going to subtract my integral from 0 to t of my removal function, r of t. And that right there gives me my total amount that will be on the beach. Now, I did make one mistake. Actually, I made 2 mistakes. So, see if you can figure out what my mistakes are, and then we'll fix them. The mistakes that I made were just with notation, but they happen to be really picky with notation. So, we do need to take a second and go back and fix it. My variable that I have as my limit of integration cannot match my variable that's inside, because this is referring to a general time. And remember, this is just my dummy variable here. So since they told me to do in terms of time, I just need to pick a different variable and use that as my dummy variable in here. And then the other thing I forgot is I forgot my dx. And that's just good habit, and it's easy for us to forget, but it's good habit to make sure we're writing our integrals correctly. And if we go back to the concept of an integral, I have some height times some width. Dx represents my infinitesimally small width. So if I go back and fix this, I apologize for my phone keep ringing. If we go back and fix this, we're going to have, let's see if I can erase. Nope, it's not going to let me erase. Okay, so I'm going to change this to an x, and then I'm going to squeeze in a dx there. And this is going to be an x also, and then times dx. Okay, and then that's looking really good for part B. I'm going to give you one other option here, and the other option could be that we could have written it this way. 2,500 plus the integral from 0 to t of s of x minus r of x dx. And you could have put it, we should put, of course, parentheses around all of that. But you could have put it into one integral. There's not a better or worse, they're equivalent, so either one of those works. It goes back to our properties of integration. That was 3 points there, just so you can keep track of your points and where you would be getting points. 1 point was for the integrand, so either having this or those two gave you 1 point. Remember, you had to have the x there or some other variable besides t. 1 point was for your limits of integration, so if you had correctly put 0 and t, you would have gotten a point for that, and then a point for your answer. So the third point would have been for having the entire thing, starting with the initial amount, 2,500, and then adding your rate of change and subtracting your other or putting your 1. So that would have been 3 points there. Okay, clean screen, we're going to finish this up. Part C and D. So far we have 2 points for A and 3 points for B. Part C. Find the rate at which the total amount of sand on the beach is changing from time equals 4. At time equals 4, sorry. So we want to find an instantaneous rate of change for the amount of sand. Recall that our amount of sand is our function. Oh, cool. Okay, so we just did in part B. I'm going to rewrite. You're going to follow what I'm rewriting. 2,500 plus integral from 0 to t of s of x dx minus integral from 0 to t of r of x dx. Here's my function for the amount of sand. So that was part B. Part C, they want me to find the rate at which that amount is changing. So isn't that just a derivative? We're in calculus class, and when we're finding a rate of change, we're finding a derivative. So they want us to find y prime of t. So they want us to take the derivative of the equation. On the left side, just look at what I have. I have y, and then I have y prime of t. That means that I just took the derivative of y. Another way of saying that is derivative of y of t. is the same thing as y prime of t. So I took the derivative of the left side. Guess what I got to do on the right side? I got to take the derivative of the right side. So derivative of 2500, that's just a constant. So derivative of a constant is 0. Derivative of an integral, interesting. Okay, so I wrote it out the long way. And you don't necessarily need to write this out, but I wanted you to recognize what we're doing here. And hopefully that's at least looking familiar from the last time that we were together. And we did something that we called the second part of the fundamental theorem of calculus. And we're taking the derivative of an integral, and you're thinking, well, that's interesting. They're just going to cancel each other out. So recall that our conclusion, kind of our shorthand of what's going to happen here, is that this variable, as long as it's just a variable, we don't have a function there, it's just a simple t, is going to go inside. And my derivative of my integral is going to give me just a simple s of t and r of t. And the 0 is going to go away there, so I've got y prime of t is going to be s of t minus r of t. Now, possibility that you got that a little bit quicker. I wanted to show you how that's connected to what we did in part B. But you could have certainly gotten that just by saying the rate at which the amount is changing is my rate at which it's being added and the rate at which it's being removed. It's the difference between the two. And that's really all we have there in part C with our y prime equation. So if you didn't do the whole integral part here and you skipped all of this, and you just said, oh, I know what this is saying, and you got right to there, you would have gotten full credit for that, okay? And of course, the initial amount doesn't matter when we're talking rate of change. They want to know at time 4, so I'm going to do y prime at 4. And now I'm going to go to my calculator, and I'm going to plug in my calculator. S of 4 minus r of 4. I already have s and r in my functions. y2 and y1, make sure you get the correct one. So y2 of 4 and minus y2 of 1 is what I'm doing. I would type it in my calculator exactly like that because then it's going to preserve the accuracy, and I'm going to round at the very end. Answer check here should be getting negative 1.909. And they are looking for... didn't say units. It's always a good idea to put units. The rate at which the total amount is changing. So I'm back to rate equation, yards cubed per hour, I think is what it was. Cubic yards per hour. So I'm going to throw the units there, and that one is just 1 point, folks. 1 point because there wasn't a ton that we were doing. And like I said, we didn't really totally need to use calculus there. We could have jumped to our equation. So part C, we've got 1 point. Then by process of elimination, we know that part D is going to have to be 3 points to get us to our 9 total. So part D, let's take a look and see what we've got. Find the time at what time is the amount of sand on the beach a minimum between 0 and 6. Notice we're including 0 and 6. So we do have endpoints to consider. It could be 0, it could be 6, or it could be any time in between. They're asking what is the minimum value? Justify your answers. So if we just remove the problem situation here and read this question and think, what calculus concept are they talking about here? I'm seeing the word minimum, and I'm thinking absolute value, absolute minimum or maximum, in this case a minimum. They're asking for both. They're asking for at what time and what is the minimum value. That's what a lot of you have been missing, the part of what's the minimum value. You've just been giving me the at what point in time or at what x value does it occur. So let's make sure we finish up the question. I'm sure that's going to be a point there to get to the final answer. So how do we find a minimum? That's the question. And I'm guessing a lot of you are thinking derivative right now. That's cool because we've got our derivative equation right here. Derivative equation, here it is. So derivative, how does a derivative help me find a minimum? Well, I want the minimum of y the amount, but the minimum is going to occur where the derivative is equal to what? You got it. Derivative is equal to 0. So I've got to find where my derivative is equal to 0 would be the easiest way. Of course, if you wanted to graph this, you could totally find a minimum on your calculator. I think that's going to be pretty hard to graph. I'm not even sure if my calculator wants to do that or can do that. But this is a very easy function to graph, and I could find where that's 0. So here's what I'm going to do. I'm going to go ahead and type in my calculator. I'm going to make a y3 and make that y2 minus y1. And then I'm going to graph that. And I just graphed the derivative graph. So I'm going to take a look at my derivative graph. And I'm going to find when is my derivative graph equal to 0. Pause the video and go ahead and do that. Okay, so now that you were able to graph that, hopefully you have an answer. Just a quick reminder that we should be in radian mode. I went ahead and did time 0 to 6 because that was my time interval, and I didn't mess with the y values. I just had -10 to +10. It worked out okay. So sometimes you have to mess with that a little bit, but I wouldn't waste a ton of time if you're thinking that this is ultimately a time question. Here's what I had going on with my graph. I have, just to give you a quick view, I had something like, and another way you could speed up the process here is kind of weird looking graph. Does something like this and then goes up right after. Here's 5 right about here. Actually, 5's a little closer to. It's almost intersecting at 5. You could have turned off your y1 and y2. So this is y3 that you're seeing right now that's in black. And I didn't really care about the others. And I calculated the 0. For my 0, I got time equals 5.118. And we're talking hours here. Now, I'm just noting this so that you can double check your answer. I did not write this down and use this answer. I mean, it doesn't hurt to write it down, but I would make sure that you use more accuracy. So right now, I would go ahead and go to your calculator. I know we've done this at least once, but it's been a while. I would go to your calculator, do second quit to get to your home screen, and then type in these commands. X, store is the button right above on, and then do a letter. So I just hit A, alpha A, hit enter, and it should spit out that number that you had gotten for your x-intercept of 5.118 hours, but it's going to have all the decimals, and it's now storing the exact answer rather than the rounded answer or you having to type in all the decimals. Okay? So what we just figured out is and let's go back to this. We're looking at a derivative graph, folks. So we're back in chapter 5, and we're looking at a derivative graph, and talk about making some connections here. Let's think about what's happening on my derivative graph. Well, my derivative, I don't like to use D for derivative. Let's use y prime because that's what it is. My y prime is 0 at this 5.118. And my y prime is going from negative values to positive values, which means my function is decreasing and then increasing. I'm talking about my y function, which I didn't graph, but my y function that's giving me the amount of sand on the beach. So they're saying, at what point is your amount a minimum? It looks like it's going to be right at this value. Okay? Now, unfortunately, the AP test doesn't really go with, hey, you just thought through all that. They have no idea what you were thinking, and they won't just accept it if you give them time equals 5.118. They want you to know you have to provide some kind of justification as to why that's the minimum. So there's several ways to do this, but I would say the easiest way, and then of course we need to get the amount. The easiest way is to do both of those at once and do a little bit of a table here. So the table that I would make would be very simply, the table that I would make would be this. It would give a time value and it would give a y value, which is my amount of sand on the beach. And this is the same thing I told you for checking absolute values, no matter what it is, to give yourself your minimum or your endpoints, which are 0 and 6, and then give yourself your amount, which is 5.118, your critical point. So here's my critical point. And here's my endpoint and my other endpoint. And what we established in Chapter 5 is that your absolute minimum has to occur at one of the endpoints or the critical point. Now, we have a pretty good idea from our function analysis here that it's going to be at that critical point, but what the heck? Let's just make them happy, and let's go ahead and figure out what our y values are. So how am I going to get y values here? Well, recall that your y function is established up here in blue, if you can see what I wrote for part B. So go back to part B. Your y function is the amount when we've got 2,500 initial amount plus your integrals of your rates of change. So you are going to have to use that function. And we now know that for our amount t, we're going to be putting in our 5.118, but hey, we stored that as a. So what I would do is type this in your calculator, exactly what we have right here, all of that, but for your upper limit of integration, make that an a, and make that an a. And if you type that in your calculator, go ahead, pause, type that in your calculator, you're going to get an answer of, big answer, 2,492.369. Now I can round because this is my final answer for the amount of sand on the beach. So that's going to be cubic yards. And then I'm going to do the same thing, but I'm going to type in 0. Oh, wait. If I'm going an integral, think about it. An integral from 0 to 0, if I make that a 0, integral from 0 to 0 is 0. There is no change in there, so that's 0, and I just get 2,500. So this would be 2,500. Okay, looks like I'm definitely below that when I'm at 5.118. And then I got to type in 6. So let's go back up here, make that a 6, make that a 6. Second enter command on your calculator gives you that same entry that you just had, and all you have to do is change that limit of integration. And that's going to give you 2,493.277 cubic yards. So now I have a quick way of comparing, and I'm looking at this table that I made in black. And that is going to be, they do accept that as justification for, you found your critical point. That was 1 point, by the way. You set y prime of t equal to 0. So we did that in our calculator to find our critical point. It wouldn't hurt if you jotted that down on your paper and said, find when y prime of t equals 0, and then put time equals 5.118, or put a few more decimals there. And then your third point is going to be from your actual answer. So actual answer would be including all of this. I know I made a total mess of this page, but let's get everything out of the way here. And my actual answer for part D, I suppose I'll show you everything that I would have put on my page. So this is what I would have put to show my work of what I was doing. Then, of course, I would have put my table down here, and then I would have put conclusion. The amount of sand is a minimum when t equals 5.118 hours. The minimum value or amount of sand is 2,492.369 cubic yards. I'm not just going to leave it in the table and let them figure it out. I'm going to say, I know what I'm doing. Here's my answer. And I'm going to finish it like that. Sorry for the length of that problem, but hopefully that helped you really understand what was going on there. So your job is to now try question number 2 in your packet. It's very similar. I'm going to give you 2 heads up when you get to question 2. The first heads up is going to be that you are not starting at time 0, and they tell you that right in the problem, but just be aware that you're not going to have a lower limit of integration of 0 because of the situation that's going on. And the second heads up I'm going to give you is that part B, because you're talking about figuring out a price or an amount of money collected, it's going to be a little bit different. Remember that your integral of a rate gives you the amount of something. So that should help you, and then just think about the problem, and I think you'll be able to get that one. Very similar as far as the rest of it goes. So take a look at that one, do your best, and see how far you can get on that.